So today I'm going to be talking about forms in many variables. So by a form, unfortunately I don't mean an automorphic form. I mean a homogeneous polynomial with integer coefficients. And everything I'm going to say is going to be joint work with Tim Browning from the University of Bristol. Okay, so a quick sketch of what I'm going to talk about. So first I'm going to, at the risk of patronising most of you, I'm going to introduce the Hasse principle, more for my own sake probably. Then I'm going to talk about two theorems, a theorem of Birch, Brian Birch, and a theorem of Wolfgang Schmidt, about forms in many variables, and how you prove a Hasse principle. And then how people have improved special cases of Birch's theorem. Then some general improvements in Birch's theorem. And finally, the methods that go into obtaining these general improvements. Okay, so the Hasse principle. So here's a famous theorem of Minkowski. And it was later generalized by Hasse from the rationals to number fields, and hence the name, the Hasse principle. So what does the theorem say? It says if you take a homogeneous polynomial with integer coefficients, and its degree is at most 2. So it's either linear or quadratic or constant. Then the following are equivalent. So f has a non-zero solution in the rationals, if and only if f has a non-zero solution in every completion of the rationals. So specifically in the real numbers and in the p-adics for every prime. So we'll call this a Hasse principle when such an equivalence holds. And the question that I want to address today is, does this still hold when the degree exceeds 2? Unfortunately not. So here's an example. There are lots of examples. Here's one due to Selma. And it's a very simple looking cubic form. And it's got non-zero solutions in every completion of Q, but it doesn't have non-zero solutions in Q itself. So the Hasse principle fails in general when the degree exceeds 2. And one can explain why the Hasse principle fails for this example due to something called the Brouwer-Manin obstruction, which I'm not going to go into. But for certain forms, so forms which are sufficiently non-singular and in sufficiently many variables, this Brouwer-Manin obstruction shouldn't exist. And so there's a conjecture, is due to Colliot-Telen, that when your homogeneous polynomial is non-singular, so I'm going to define that in a second, but when it's non-singular and the number of variables n is at least 5 and at least the degree d plus 1, then the Hasse principle should hold. So there's no Brouwer-Manin obstruction. So I want to talk about steps towards this conjecture. But first, what's this singularity condition? So a non-singular form is one where the first partial derivatives don't vanish identically on affine n space, apart from at the origin. Okay, so you can cook up examples from Selma's example, which also fail to satisfy the Hasse principle. But the problem is this is a very singular form. So it's certainly non-singular, but in fact if you look at the set of singularities, so the set of points where all the partial derivatives vanish, then it's actually a very large set. It's got quite large dimension. I'm wondering if I stand away from that mic. Well, is any better? Okay. So this is highly singular. So it's a very natural condition to impose some non-singularity constraints on your homogeneous polynomial to try and obtain a Hasse principle. So now here's Birch's theorem, but first I need to introduce this set I was just talking about. So the singular locus is the set of points where the partial derivatives vanish identically. We're going to use sigma to denote the dimension of this set. And sigma will always denote this dimension throughout the talk. So here's Birch's theorem. You take a form f of degree d, and you suppose that the difference between the number of variables n and the dimension of the singular locus sigma is strictly greater than some function of d. Here it's d minus 1 times 2d, 2 to the power d. If you think back to Collier-Tollen's conjecture, when a form's non-singular, then sigma is equal to 0, and so the conjecture would be that n is strictly greater than d plus 1 and greater than equal to 5. So this is kind of an approximation or a step towards this conjecture of Collier-Tollen, but it's exponentially larger than we'd like it to be. Nevertheless, it's one of the few general results of this type which proves a Hasse principle for forms of general degree. But there's one more theorem of this generality, and that's due to Wolfgang Schmidt. And we had this dimension of the singular locus, sigma, so that's an invariant of your form. But you can have a different type of invariant, the so-called H invariant, and that's the minimum H such that you can decompose your form into a sum of products, H product, so into a sum of H products, where each factor of the product has degree strictly less than the original form. And so in the mid-80s, Schmidt proved that provided the H invariant is sufficiently large in terms of D, the degree of the form, then the Hasse principle should hold, or does hold. So these two theorems are the only theorems of this kind of generality for forms of general degree. And they form kind of cornerstones for lots of other research. So here's lots of research which kind of stems from these ideas. I don't expect you to read this slide just to take away the impression that people have worked on extending and specializing and improving these results. But there's still no improvements in Birch's theorem for general D. There are lots of improvements for small d, small degree forms, particularly for cubic forms. So if we assume, just for convenience, that f is non-singular, so sigma is equal to 0, and in fact that's the generic situation. If you take a random form, it's going to be non-singular. Then the Hasse principle holds, provided, well, Davenport obtained that cubic forms in 32 variables satisfy the Hasse principle. And this is kind of the result that Birch generalized to obtain his theorem in the early 60s. And if you substitute sigma equals 0, d equals 3 into Birch's theorem, you get 17 variables. And then Davenport managed to shave a variable off Birch's result. And then there was a quantum leap in the early 80s where Heath-Brown shaved 6 variables off Davenport's result. And this used lots of new ideas. So cubic forms in 10 variables satisfy the Hasse principle. Well, the local conditions are automatic in 10 variables. So in fact, all cubic forms, non-singular cubic forms in 10 variables have a non-zero solution. But in 9 variables, the local conditions aren't so straightforward, and Hooley proved a Hasse principle for 9 variable forms, cubic forms. Okay. In quartic forms, well, there's a much sparser set of results here, and in fact, Birch's theorem was the record. Birch requires n minus sigma to be at least 49, and that was the record up until 2009, so almost 50 years. But in 2009, Tim Browning and Roger Heath-Brown saved an extra 5 variables over Birch's result. And then Hanselman, in his PhD thesis, utilized an extra idea to save another variable. But that's it for quartic forms. There's no more improvements. And for quintic forms, degree D higher than 4, so 5 onwards, there's no improvements. So what does Birch require for general D? We need m minus sigma to be at least 1 plus d times 2 to the power d, so that's our main term, d, 2d. And then we've got a saving of minus 2d, a lower order term which is a saving. And recently, myself and Tim Browning, we managed to improve this. Not the main term, d2d, but we can make an extra saving in the lower order term. So we can put a factor of root d over 2 times this lower order saving. Yeah, so just to state it again in concrete terms, if you've got a form of degree d, its singular locus has dimension sigma, provided m minus sigma is at least this function of d, then the Hasse principle holds. So to be even more concrete, let's look at some numbers. So here's Birch's bound in the left column. That's the number of variables Birch requires for the Hasse principle. And this is the number of variables we require. So for quartic forms, we save a variable over Birch, which isn't so good. But for degree 10 forms, we're saving thousands of variables, which is nice. But you can see these improvements are really weak when d is small. So when d is 4 or 5, they're not particularly good improvements. And when d is 3, it's a negative improvement. We will require more variables. So not very good for cubic forms. So we tried to work on improving for small degree forms as well. And we can do substantially better when the degree of the form is small. So provided the degree is between 3 and 9, we can actually improve the first order term in Birch's theorem. So now our bound is about 75% of the size of Birch's bound. So we need 3/4 d2d minus a lower order term. Okay, so again, let's be concrete about it. Let's do our bookkeeping, see how well we've done. So we obtain the Hasse principle for cubic forms in 13 variables. It's not quite Browning and Heath-Brown, which need only 10 variables. And then for quartic forms, we actually reprove this result of Browning and Heath-Brown. But we don't do as well as Hanselmann. And then for degree 5 and more, all these results are new in the rightmost column. But the methods in the rightmost column, they break down when the degree is 10 or more. Okay, so the methods. So we use Fourier analysis, or the circle method as developed by Hardy, Ramanujan and Littlewood. And how does the circle method work? I'm sure many of you know, but here's a quick sketch. So you take a generating function. And here our generating function, it's we're going to sum over all integer points whose coordinates are between 1 and p. And then we take some exponential function, e to the 2 pi I, raised to the power alpha. Alpha is a real number, a real number. And then we evaluate our form f at this integer point. And we've got this nice identity, orthogonality, that the number of integer points whose coordinates are between 1 and p, such that when you evaluate f at this integer point, you get 0. This is equal to the integral from 0 to 1 of your generating function. And the strategy of the circle method is to decompose the interval 0, 1 into 2 sets, which you can handle by different means. So you decompose the integral into an integral over the major arcs, that's large M, capital M. And you can think of those as real numbers which have a good rational approximation. And then the minor arcs, little m, that's just the complement of the major arcs. And so here's a kind of hand-wavy description of what the major arcs are. It's the set of alpha between 0 and 1, such that when they're close to a rational, a over q, by about epsilon over q, where epsilon we're kind of free to choose, and q is small, but I won't go into what epsilon and small should mean. It's different depending on the employment of the circle method. But what's nice on the major arcs is standard number theory and a little bit of analysis shows that you can prove this is bounded below by some constant Cf times p to the power n minus d, something that grows with p. So as the size of our box increases, this term gets larger, provided the constant's non-zero. And the constant is definitely non-zero if f has local solutions. So if there's non-zero solutions in every completion of Q. So hopefully this is our main term, and we can show that the number of solutions grows, provided that the other term, the integral over the minor arcs, is sufficiently small. Smaller than the main term, so a little o of p to the n minus d. And proving this is standard, as I said, but this is where the bottleneck occurs. This is where all the improvements that I've listed in various cases of Birch's theorem, obtaining this for less and less variables is where the improvement comes from. So this is the bottleneck, and all you can do is bound it pointwise. So I'm just going to sketch Birch's approach to bounding this pointwise, and it uses vowel differencing, and then I'll talk about our modification of Birch's approach. So this is a very standard trick in harmonic analysis and number theory, vowel differencing. Enormously useful. So what do? We square our exponential sum, and a little manipulation shows that you can relate your exponential sum of degree d. So this is an exponential sum over a polynomial of degree d, and you can relate it to an average of exponential sums. But the important point is these new exponential sums, they're over polynomials which have degree at least 1 less than the original exponential sum. So this is degree d. This is an average of sums of degree d minus 1. And you iterate this. So if you do it d minus 1 times, you're eventually relating your degree d exponential sum to an average of linear exponential sums. And we know how to bound linear exponential sums. It's easy enough. So that gives you Vowel's inequality in this context, and that's what Birch uses. So what do we do? Well, it's another amazingly useful thing is van der Corput differencing in harmonic analysis and number theory, and it's a generalization of Vowel differencing. And it starts from it starts from a tautology, and maybe that's why it's so useful. So you can shift your original exponential sum. You can perform a change of variables. So here, we're averaging our original exponential sum shifted. But this is just our original exponential sum hn times. So there's no content there. But once you square and apply Cauchy-Schwarz and rearrange just as you would in Weyl's inequality, you get a similar consequence. You relate your degree d exponential sum to an average of exponential sums of degree 1 less. But the difference here is in Weyl's inequality, in Weyl differencing, it looks pretty similar, but after van der Corput differencing, our averages, the coordinates of our little h, are restricted to be between big H, minus big H, and h, where h is some parameter between 1 and p. In fact, we can choose any h between 1 and p. And in Weyl differencing, h is forced to be p. So that's the only difference. But this is quite a lot of freedom, because we've now got the freedom to choose h according to the situation. So that's the advantage we exploit. So again, you do the same as you do in Weyl differencing. You iterate this, and you relate an exponential sum of degree d to one of degree d minus k if you Van der corporate difference k times. And what's nice about this exponential sum of degree d minus k is that you can control the height of the polynomial according to these parameters h1 up to hk. So that's useful. So instead of going down to a linear exponential sum, as we did in Weyl differencing, we're actually going to exploit different exponential sum estimates for different degree exponential sums, and then take all of these estimates together, take their infimum, and hopefully we can beat Birch's Weyl bound. So we exploit every known estimate, and we do Van der corporate differencing for every value of k between 0 and d minus 3. But our main estimate, and the most efficient estimate, comes from Van der corporate differencing down to a cubic exponential sum. And we can get good bounds on cubic, after Poisson summation for cubic exponential sums allows us to employ Deline's bounds, which are very efficient. And this actually covers most alpha on the minor arcs. That's our main estimate. But unfortunately, it doesn't cover all alpha on the minor arcs. So we don't have a good pointwise bound for our exponential sum on the whole minor arcs. And that's why we have to make these other estimates. So I'm going to kind of hand wave about how we exploit every known estimate. So bear with me. So first you take alpha in your minor arcs, and then you perform a Dirichlet kind of Diophantine approximation. You obtain an integer q, size at most big Q, such that the distance from q alpha to the nearest integer is at most 1 over q. Now big Q, it's some parameter, again, we're free to choose it. But every alpha in the minor arcs has such an approximation. And the important point is that for alpha on the minor arcs, you can deduce that at least one of q and this quantity can't be too small. So there's some Diophantine condition for alpha in the minor arcs, which you can see through these q and q alpha. So either q is large, greater than some constant c, or q alpha is large, greater than theta. So what do we do when q is large? Well, this is where we Van der corporate difference to a cubic exponential sum and apply Poisson summation and Deline's estimates. And that covers almost all the minor arcs. But when we don't have this estimate for q, so q is necessarily small, then we know that q alpha is between theta and 1 over q. So we break that interval between theta and 1 over q. We break it into subintervals. And then depending on where alpha lies in these subintervals, we apply a different estimate. So when q alpha is between theta and is in our first interval, the smallest interval, we don't Van der corporate difference, we just apply Weyl's inequality as Birch did to a degree d exponential sum. And then in the next interval along, we Van der corporate difference once, and then we get a degree d minus 1 exponential sum, and that again we estimate using Weyl's inequality, and we just keep going. So in the next interval along, Van der corporate difference twice, then we estimate our degree d minus 2 exponential sum using Weyl's inequality. Continue iterating this until you get to the last interval, and that's when we Van der corporate difference back down to a cubic, as we did in our main case. But now we don't apply Poisson-Deligne, we apply Weyl's estimate to a cubic exponential sum. And this strategy, well, it's a lot more complicated than it looks here. Actually, each case here, I'm not applying one estimate, I'm applying all the previous estimates combined. But for convenience, this is kind of how you should think of it. And provided that there are sufficiently many variables, this strategy works. It covers all alpha in the minor arcs. Unfortunately, it doesn't, for this number of variables, it doesn't work if d exceeds 9. But if we give ourselves a few more variables, then the strategy does work. It manages to cover all alpha in the minor arcs. And how many variables do we need? Well, it's this amount, asymptotically. So for D10, 11, 12, you could improve this, but we were just interested in what does this bound look like asymptotically, and you couldn't improve the main term, but you could improve the lower order term, asymptotically in D. Yeah, so that's all I've got to say, so thanks for listening.